You just want to do that. Is that right? There we go. Now everybody online is getting the same thing. Can everybody hear me over there on the internet? Do we get a message back?
Yep.
Yeah, okay, cool. Yeah, great to meet all of you. Thanks, Andre, for inviting me to present. Yeah, kind of my, kind of communication style around AI and machine learning is kind of focused on, not hitting you over the head with a bunch of like marketing stuff, and really just kind of talking about, how to actually make use of the technology that we have, trying to be honest about the technology we have and the technology we don't, and just kind of going through a lot of the hard work around AI, which is, I always like to say, to Andre's point, is really just a new name for machine learning and data science, which is really just a new name for statistics, right? So there's nothing super crazy about what we're doing, except for that we've built on top of work people have been doing for years. But yeah, and so I have a newsletter where I kind of take that view and just kind of write about the things that we're thinking about. And I think this year I am going to focus more specifically on AEC topics as well. But yeah, so this is me. A little just background on myself. Starting kind of from the beginning of my professional career, I started a startup to try to build essentially a sim city for real cities. That was very hard to do, and it didn't work, but that was fine because I learned that I really enjoyed data science and statistics and all that was involved with that. So then I hopped over to a startup called Carbon Yield, where I did remote sensing, machine learning on satellite imagery to do classification of different farming practices, which was super interesting. Then went to a firm called Swell Energy, where I helped develop their virtual power plant system. So co-optimizing thousands of at-home battery storage and solar to work together to operate as a power plant together, so that folks like who is like the city of San Diego could call us. Actually, Queens could call us as well for an actual power event as a peaker power plant, and all of this sustainable energy would be put on the grid from those houses. And then I came to DLR Group to kind of head up their design-focused data science work about 2.5 years ago. And I studied at USC, and I got a degree in geodesign, which was kind of data-driven architecture and planning. So that's kind of, I had a little bit of intuition around this from that, and so this was kind of a bit of a full circle moment for me to kind of bring that skill set back into like a problem area that I really enjoy. Okay. So I love this whiteboard art that somebody did once. I found it on the internet. I don't know who they are, but this is beautiful and brilliant. And I think the best way I have to describe what AI and data science is, which I think is a good place to start. It's not right. It's not something that really knows anything that it's talking about. It's also not really an entity or a thing. It is the combination of all of these kind of individual skills, individual areas of study, practices, and I like to point out that the stuff that's advertised as like AI and machine learning is everything at the bottom right of this, right? It's like deep learning, CNNs, RNNs, a little bit of random forests. But to get there, you have to do all this other stuff first, and do that well if you want the stuff at the bottom right to work. And so we're talking about software, we're talking about data cleaning, we're importantly talking about data ethics, we're talking about statistics. I think linear algebra is not on here. I would put that on there as well. But all of this together is AI and data science and machine learning. And this is why it can be quite hard to get these systems to work. It's because all of this has to be working together. And so let's see here. I want to go to the next slide. Okay. But so obviously that was a lot of different things to keep track of. So something that a way I like to think about this, kind of, especially if you have kind of somebody's coming to you with a problem that they want, an AI system or a machine learning system to solve, I kind of try to bucket them into these kind of 7, and there could be 14, there could be 5, depends who you ask. I like this group here of 7 machine learning typologies. And I like them because once you kind of know which typology you're going to use, usually there's a lot of alignment in terms of what types of data sets you need, how you need to label your data, what types of models you're going to actually use. And so, if I know that something is going to be a segmentation problem, I now know the whole body of research I can go to. I know all the old software that I've used before to do segmentation that I can use again. And I'm going to kind of, you're going to see some of these icons throughout the presentation to kind of remind you, and I'll call it out too, but just like each one of these things I show does fall into one of these. And pretty much every machine learning system or AI system also falls into one of these. And especially if you're evaluating possible tools you might want to use, it's helpful to be able to think, okay, that's an optimization problem. So I kind of know how it works maybe, its limitations, what it's actually trying to do, and importantly, what it's not trying to do. And so with those 7 AI kind of top typologies, I always kind of go through this process of how to kind of listen out for key phrases, key asks, and connect those back to those typologies. So, oftentimes I get asked, I want help finding the best. Like, I want the best layout for this floor, this floor plate. I want the best HVAC system for this building. And that is an optimization problem, right? And so there's a whole toolkit that we can now use because we know it's an optimization problem. I want to be shown new options is generative, right? And so there's a whole set of tools that you can use there. I want to be able to search by. This is a little kind of unexpected, but that's usually classification because people want it to be labeled so then when they search by it, it comes up when they ask for it. I'd like to detect is usually segmentation. I'd like to translate is usually something we call encoder-decoder architecture. I want to find something like this, which I actually think comes up all the time, is similarity, a similarity analysis. And I feel like people don't really write about similarity analysis that much, but it actually underpins ChatGPT, it underpins diffusion models, but that's and a lot of the examples I'll show kind of fit into that too. Okay, so I wanted to share a little bit of the stuff that we've been working on at DLR Group, and then I'll kind of go into some of the things we've been thinking about that I think are interesting to kind of engage everybody here on, especially. And this is just as you kind of think about some of the ways you can kind of put some of this thinking into practice. This is some examples from a project that I worked on with the School Construction Authority of New York here. And so they were interested in meeting their GHG reduction targets, I think by 2030, if I can remember correctly. And so kind of the question is, we have 1,600 buildings. And we have to renovate some of them in some way to meet these targets. So how are we going to do that? What are the right renovations on the right buildings? How much is this going to cost? How do we make these decisions? There's, truly millions and millions of variables to consider. And so our engineering team worked with them to build on what's on the left here for looking at it, this decision tree. And so this essentially takes different data points that we have on each building about its quality for different systems. So like we know its HVAC quality, we know its like parapets and its roof quality, right? And you can kind of go through this tree, and at each of these like kind of intersection nodes, I'm colorblind, so I think they're red or orange. I don't know. The ones at the bottom that are a different color? Green, thank you. At each of those, there's essentially like a cutoff. And so if it's above a certain value or below a certain value, it's going to go in a different direction. And so the team worked for a long time to figure out, OK, what are the exact cutoffs we want? And then when you pass every building through it, you get essentially a renovation is recommended. And there's a cost associated with it. And there's a GHG reduction associated with it as well. And so that was cool. But then the client was like, well, what if these cutoffs aren't right? What if we're spending too much money in the wrong places? And so what we did is we essentially turned that decision tree into a simulation. And we simulated essentially the outcome across all the different cutoff settings you could have for every single building. And then kind of aggregated up those statistics to build the dashboard that you see here. And so this is one way of solving an optimization problem, which is, it's a little bit of a messed up Monte Carlo simulation. But once we had simulated all those options, now they could just slice through the results of their simulations to find the ones they really liked, right? They could say, I only want to spend this much money, and I want to maximize my GHG, or I want to maximize my GHG, I don't care how much money I spend. And then just find the settings that achieve that and figure out all the renovations that their building should go through. So yeah, that was kind of in the optimization realm. We have a project that we've been working on for a little over a year. A lot of folks are working on this. We're also working on it because the people who are working on it want to charge a lot of money, which is fair. It's very hard to do. But we're trying to, or we're helping to automate the process between scanned buildings and representing those buildings as Revit models. And so this is if you look up at the top right, this is a segmentation problem. And so we're using tools that are kind of in our tool belt for segmentation to teach the computer to identify chairs and walls and ceilings, tables, kind of all the things you can see there. And then we bring that into Revit. And it's not perfect, but something I try to drive home about kind of AI and machine learning systems is if it needs to be perfect every time, don't use these tools. But if you need it to be really close 95% of the time, then these are really good. And so that's really what our aim is. Then people can kind of go through and make some final tweaks. But the goal is to at least get them 50% of the way there, 70% of the way there. So that's what we've been working on there. I hope this could be a video. Yeah, this is something I've been working on lately, and this is a kind of a demonstration of our detail recommendation system. So we've been starting to get into kind of the realm of Revit recommendation systems. As we have at DLR Group, we're lucky to have probably 500 new buildings every year that we at least complete Revit models for. Whether or not they get built, that's past what I worry about. But so we have this huge vat of information, and we've almost always done something like this before. And I think probably a lot of people have that experience. And so as part of our effort to really kind of like surface all this institutional knowledge we've been working on, these different recommendation engines. And so in this example, we have kind of two types of recommendations that this provides. First is kind of a alternatives recommendation. So you can take, and this is for details, right? So somebody's placed a detail, and then we can go through and we can see, are there other similar details that maybe you should just check and make sure one of these isn't better for your use case? Or especially if we have certain details that are, might have certain earthquake ratings or certain sustainability components to them, where they're effectively, for code standards, the same thing, but they just use a slightly different material. We can just directly kind of
Revit user group
identify that
giving a presentation of all of our tools and our automation stuff.
And then on the bottom, it's providing
really, we have these tools?
recommendations. So based on, once you've placed a detail, it tries to determine what the other likely details are to be that you're going to use on that same sheet. And so it's kind of trying to bring all of this to you quickly. And again, right, the goal isn't for it to be perfect. It's to show you maybe two more that you were going to look for anyway. And instead of you having to go find it, it's just there for you. And these are demo boxes, but it's using all the data infrastructure. And we're working on bringing it actually into Revit, which hopefully the next time I present one of these, I'll have something like that. Cool. And yeah, the other cool kind of recommendation system that I've been working on and I'm excited about is around element placement. And so I think the big thing that works here is it has this recommendation system. So this is for a classroom, and it's placing electrical outlets. And so what is kind of cool, well, the thing that and so you can notice in the top right, it's two things. It's a similarity problem, and it's an optimization problem. So the first thing, which is kind of showing here, is the task of how do we figure out like what rooms are like this room, right? Because we've done classrooms before. And the question is, well, it has to be the right shape classroom. It has to be the right size classroom. And then from there, we can kind of show these options. And then it's an optimization to actually place it right in the right place. But so this is just a demonstration really of the similarity component. But it actually finds like the right types of other rooms, which I thought was really cool. And so that's what this is demonstrating. And so to do this, we really had to actually figure out how to communicate shape to a computer, which was not as easy as I thought it was when I said I could do it. And this is kind of a typical use case that people will talk about, but this is just an example. We have started integrating kind of a chat-based assistant into Revit. And so this is having it place something. And I don't remember exactly what it is actually in this video. I think it's room numbers, or it's interior elevations. Ah, there it is. And so I think something, the thing that I like to bring up with this, but this isn't actually as complicated as it looks, right? We already had a tool that placed elevations that people didn't really use as much as they maybe could have. And so this is just putting it inside of this assistant. What we can do is we can notice the times that they should use it, which is really powerful. And then we can just say, hey, this is usually when people do elevations. We have this elevation tool, right? We can say, do you want to place the elevations now? And then they can do that. But it's still using, the computation work that, a lot of folks have been working on for a long time. But it is a good example of kind of how you can use machine learning systems to kind of work in concert with what you already have. It doesn't really have to be something so new. Cool. Yeah. So I wanted to kind of share a little bit about, kind of in my effort to not just talk about like, this super cool stuff, but talk about, some of the problems we're having, some of the things we have to think about, kind of really the nuts and bolts of where we are, especially in this industry for data science and AI. I wanted to share a little bit about one particular investigation that we're kind of going through. And I'm hoping some of you guys might have ideas. But the big question is how to represent AEC data for a computer. And I'm going to go through what the heck I'm talking about when I say that, because I think it's not, this is one of the more, one of the harder things to wrap your head around when you start learning about machine learning and data science. But we kind of represent naturally architecture and AEC in a lot of different ways, just naturally, right? We have BIM, and so that's kind of, we have these objects, and they have some relationships, and they have location, and they have shape. We have sketches, right? That's on 2D, but there's obvious 3D implications of sketching. We have like schematic details, which is an image, but it's really a lot more than an image, because line weight really matters, and there's all these other components of it. We have spec sheets, which is text representations of architecture. We have like physical representations of architecture in 3 dimensions. And so that's like planes and volumes. And then we have, kind of our like meshes and our wires, which is kind of volumetric as well, but you can have other things like splines and, right, it can get, there's levels to that beyond just volume. And so we have to figure out like how to have this make sense for a computer. And so I just want to, I'll explain a little bit about what I mean by represent. So these are some common ways to represent. It's really representing information to computers. And so the task is kind of like, how do we do this for architecture? And it can, right, it might be combinations of these things, it might be different things altogether. But so just to kind of introduce it, on the top left, we have the way to represent images to computers. And so we see, right, pixels is, pretty common. Obviously, we don't see pixels, but like computers show us pixels and we see things in the pixels. But pixels are pretty naturally already numbers, right? They're RGB values. And so we can just really naturally translate that into numerical inputs for a computer. And a computer has to operate on numbers, right? I think we're all familiar with that. But you can't just give it a sketch. We have to turn it into numbers. And so that's a really easy way to do it. And you might notice that the things that are easy to represent, we have really good machine learning and AI for, because this is kind of the hard part. But so that you can just represent images as pixels and their values. It can be, if it's black and white, it can be just 2 dimensions, right? We have pixels in the X and the Y, and I guess that's 3 dimensions, and then the number at the X and Y. But if it's RGB, then you just have kind of like 3 levels of that. You have an R layer and G and a B. Then for text, we can take the sentence to be or not to be, and we could encode it based on what is called a token. You might have, if folks have been reading about like ChatGPT, they have token limits, and that's what a token is. So essentially, for the most part, each word is a token. Other things like N''T are also tokens because they are kind of modular. But so you could represent to be or not to be as kind of this set of numbers. Super cool. Audio is really easily represented as numbers too, because it's waveforms, and waves are kind of a natural numeric structure to begin with. You can also just represent it as just like pure data tables. So that's like a pretty common way to do it for just like housing data, right? We have an address, we have a price, we have a square footage. And then we're all numbers, but only to the computer. We're only numbers to the computer, but that's because it has to be that way, not because it says anything about any of us. And so I think it's important to also say just kind of like why do we have to represent this information as numbers? And I don't know if any of you all met the function machine man in school, but I did. But can anybody tell me what the function machine man is doing right now? He takes in a 1 and he gives you a 3. Anybody know what he's doing? What? Processing, maybe? He's adding 2. He's adding, yeah, okay. Fine, it can be either, whatever. You can do whatever you want. But he's figured out, he has a system that takes in a 1 and it gives you a 3. He's in the actual example, it's adding 2. So I'm just going to use that one. Right, so if I give him a 5, he's going to give me a, great, you're doing AI. You're actually just doing I, but we're gonna get the artificial part. Cool. So keep that guy in mind. So and this important is the function machine, right? Functions take in numbers and they output numbers. AI is just a function approximator, and if you want the mathematic proof for it, I can send it to you. But neural networks, which is the technology behind almost all of modern AI, are a proved function approximator. And so that's their power. They can look at data, and they can, like we can look at this guy, we can look at the inputs and the outputs and figure out that he's adding 2 or multiplying 3, fair enough, and can figure out what the underlying logic would be to represent that input-output pattern. And so this is a kind of an example, right? On the right, well, on the left we have this function, right? We have x's going in and y's coming out. Oops. Something go wrong? Hopefully not.
You're not sharing anymore.
Okay. Okay. Hopefully we're fine. Okay. But, okay, so we have x's that are going in on the x-axis on the bottom, and we have y's coming out of it. Right, and so if I put in 0, I get out 0. If I put in 0.4, I get out something like 1/2. And on the right is actually showing an AI system that's learned that function just by the data points along it. And so that is truly, that is AI. Okay, now, why does this not let me? Okay, right. And so why do we need a representation? Is because we need an input to this function system, this function machine. We also need an output, but that's for another discussion. So what are some options? So we have floor plans, so that's good. And floor plans are usually images. So we have images, so we could use images. We have tables, right? Anybody who's been, like everybody in this room who's been digging around in Revit a lot, we have a lot of tables. So that's good, that's data. We have bubble diagrams. This is another type of data. This is called graph data. It's made up of nodes and links. And so our nodes are our rooms, our links are our adjacencies or our connections. And we have text, right? We could write all this out as text. But there's some goals that we should keep in mind when we're trying to figure out how to represent this information. We want it to represent it well. And so that's what we call data or feature completeness. But essentially, we don't want it to be missing really important components, right? If I look at the data and I can't really tell what's happening, then that's not a good representation. I usually like to use the am I confused test first before I see if a computer can figure it out. If I have no idea what it is, then the computer's going to be lost. And so yeah, so that's like kind of representing that sort of layout over there. And and this table, if we instead represent it kind of like the floor plan on the right, we're gaining some important information, right? We're gaining adjacency information, we're gaining proportion, we're gaining shape, right? So those are important too. So that's kind of the way to think about this. We want to be increasing the total amount of like important information that we have and that the computer has to learn from. We want determinism in our data. So the basic idea is if I have a piece of data that's saying something, it should be saying something clear. It shouldn't be saying possibly 5 to 10 things, depending on how you read it. Right? So kind of another example with the table. You can tell I don't love tables for this problem. But that sheet could represent either of those floor plans on the right. Right? A table doesn't tell us anything about the actual relations and associations going on in the real thing that we're trying to understand. And so that kind of fails the determinism test. So I've been evaluating a lot of options, and I've found some problems with them. So the first one to take a look at, I think the obvious one, the one that I looked at first, is images, because we're such a visual industry and a visual group of people. But images are really heavily inferred. Like, we know that this is a floor plan, and we know that that's a bed and that's a toilet, but that's not like necessarily obvious without our training. The other thing is, like I said with some of the schematics, like line weight is super important, and that's not super obvious and clear in image data just like originally. And there's also, when you get down to like the relationship between pixels, which is really all that a computer has access to, right? It's not that clear that like the entrance on the left is super related to the kitchen all the way on the right necessarily. You can definitely learn it, and a machine can learn it too, but it's just that's kind of a problem with this representation, is that that's not particularly clear. It also lacks hierarchy, right? I would say that the hallway and the dining room have kind of organizational principles. Things are organized around them, but there's no way to like really encode that, or the image doesn't tell me that. I have to encode that, and I have to tell that information to the computer in some other way. But it does importantly encode shape and size and proportion, which I think we would all agree, an important part of architecture. I really don't like tables for this, but it lacks interrelationships, kind of like I was sharing before, how like I have no idea if the dining room's next to the living room, or if bedroom 1 and bedroom 2 are on the same side of the room, or whatever, right? There's no mention or shape unless we add it, which can be a lot of work, of shape and proportion and position. And it doesn't really, but it does include the ability to add just tons of metadata, right? Like we can talk about materiality, we can talk about what particular type of desk we're using, right? We have kind of infinite columns that we can add. So that's good. This is the one I've liked the most, but there's still a lot of problems with it. This is that graph representation. So this is kind of akin to the bubble diagram from earlier. And what's really cool about this is this does actually start to include the interrelationships, and we can be really specific about those interrelationships. We can have graphs that represent adjacency. We can have graphs that represent access. We have graphs that represent visual connectivity. We'd have graphs that represent audio connectivity, right? How much sound could you hear from different places? Also really interesting, like if you do certain analyses on these, like you can do centrality, and it's highly, so that's essentially figuring out like which ones of these dots is most in the middle of all the other dots. And that is highly predictive for occupancy. And so it is starting to actually tell us some architectural information. But it also has weaknesses. It doesn't have shape still. It has topology, importantly, which is kind of like geometry and shape, but it doesn't really let us know about proportion. But it also does enable metadata like tables, right? You can attach any type of information to these nodes, which is really great. And now, actually, really, this is probably my least favorite representation. I'm sorry. Text. Text says nothing about design or shape, really. We can write in how relationships exist, but that's a lot of writing, right? Kind of the signal to the noise is really high. It does enable metadata, but again, like, how does a compute, like, how do you know what it's all connected to, right? Like, how do I know necessarily that the desk is connected to this particular room? Unless I've looked at millions and millions of examples of these, which is exactly how you train a GPT model. But there's a reason that those are like so computationally expensive, and people are worried about, you know, the carbon footprint of those systems. It's because they're using super low information data and just looking at a ton of it, which is always an option. You can always just give it a bunch of really kind of mediocre data, but as long as you have just like enough of it, it's okay. But yeah, so those are some of the options. And I'm not going to tell you the answer to which one is best because we're still working on it. But that, I think, articulates where we really are as an industry in AI, which I think excitingly, but it does mean there's still work to do. We're on the ground floor. And so there's a lot of really cool work to be done here. And it's not like there's some super big giant in the field that's figured all this out that you can't compete with, right? We're pretty nascent. And I like to kind of hedge people's excitement about AI sometimes in that people like, you know, the medical industry that's seen huge impacts from AI started working on these questions a decade ago, right? And so it's not to say we can't do it in 4 years or 5 years, but like we have to work on it. We can't really just take the stuff that's super cool looking off the shelf necessarily and make it work for our use case because they're all leveraging these representations and they have the weaknesses here. A GPT model, it can't, like there's Architext is an example of a GPT model for architecture. But it was trained on a ton of data and like only on apartment layouts. So if you want an apartment layout exactly like that data set, you can use Architext. But if you want something that actually is starting to learn how architecture works and operates and what it means to put two rooms next to each other, using text is a pretty roundabout way to get there. Yeah, so that's all I got. Always remember the function machine man when you're looking at AI systems. That's all it is. Yeah, and then I don't know if this is easy to see, but I do have the newsletter. So if this is kind of interesting and you want to, you know, keep up and participate in some of this thinking, contribute, you know, definitely subscribe and yeah.
The QR codes are really big.
I know. Oh, it works there.
Is this mine or yours?
No, it's mine. I got a charger though. Here, I can give this back to you, and I'll get a charger.
Okay, he's getting a charger, and then we're going to do some Q&A. Well, he's having a heart attack over there.
I shouldn't have given that back to you. I need to do it.
That's okay. Once you're done with your heart attack, I'll hand it back to you nice and slowly.
Sweet.
So you ready for Q&A?
Yeah.
All right, so what do you got? Questions?
Let me see if there's any. Yeah.
Yeah, I got a question. How's it going, everyone? My name is Eamon Thompson. I'm an architect there in NYC, do lots of different
Not necessarily. Well, it depends. I always advocate for AI in the last resort as a good approach to take. AI in the last resort, and if you have, well, there's a lot of ways to answer that. Sometimes AI is also better because it can be a lot more time and computationally efficient once it's trained, right? And so there's situations where you might have a simulation that can do it, which is awesome because that means you get clean data, which is great. But that could take, sometimes that can take, it might take an hour or something to run the simulation, or even 10 minutes. And you could train a AI system that can do inference in, a millisecond. And so there's reasons for doing that. There are certain problems that for object detection, right? Where that's a lot of rules to write out, that AI is probably the easiest option for you. I'd also say recommendations related stuff. You can do that programmatically, but again, I have a hard enough time getting people to agree on a classification abstractly. To do it programmatically, you have to get them to agree on it in a very specific quantitative way, which it could be done, but it starts to run up against well, that might take a really long time to write all that code out. So I think that's always the trade-off to keep in mind. But yeah, I think AI in last resort is a pretty good place to be. But that doesn't, there's a lot of problems that it's still the best option. Yeah. Yeah.
Well, I have more of an
Oh.
observation.
Okay.
Go ahead.
No, I think Angie was first.
Yeah.
I was just curious, how do you even get started? Everyone knows ChatGPT.
Yeah.
I can download some ready-made AI tool. But
Yeah.
if I wanted to start making something for myself, just a very simple something,
Yeah.
how do you even begin that?
Well, I do think AI is something that definitely builds on the top of a lot of other systems, right? It's kind of standing on the shoulder of giants, and so.
Can you repeat the question?
Yeah. The question is, how do you kind of get started with AI, using some AI and kind of learning about it? Is that right? Yeah. So. I think it's important to be both. There's. It's good to be frank about this a little bit. If you want to do it really well, it is important to know some of the underlying math that supports it. There's 3 types of math I would recommend, and you don't have to be a whiz at these. I was telling Alfonso, I wasn't actually very good at math when I was a kid. But as soon as I figured out what I could do with it, I really got deep, right? And so you don't have to know all of it to begin with, but the math to learn is probability, statistics, and linear algebra. And all of those have like Coursera's, right? And you can probably learn them. Each one takes like maybe a month to get through. But if you do those, you're really going to know like pretty much all you need. And in addition to, it's good to some programming and probably some Python knowledge. But with those in your tool belt, you're going to be pretty good to go. And then I think like a lot of the, honestly, like I learned a ton through like Udemy stuff. And like you get, some of those are set up really well where like you are learning little bits, you know, learning it piece by piece, and you get to apply it pretty quickly. And like even with like a week of Python, you can like build a little calendar. And like there's people making like millions and billions of dollars with the little calendar, right? Like it doesn't have to be, you don't have to get that far before you start feeling like, oh, this is kind of fun. At least that was my experience. So I would say both, it doesn't have to be so hard, but I would not recommend cutting the corners of math and programming if you want to do it well.
Yeah, I have just an observation, but I think I always go back to the comparison of, and we had a little conversation about this, right?
Yeah.
About the wave of computational design that hit us, like,
yeah.
I mean, I go back to 15 years ago where all these guys, you know, were also involved in everything. And then went in a certain way, right? The way I see it is that the implementation was almost and I should be careful saying implementation, but it was kind of almost exponential, right? Mm-hmm. And then eventually it started like, you know, going a little bit down and settling somewhere. Yeah. Now, there are serious questions about, did that bring any benefit to the AEC industry, mm-hmm. or vice versa, right? And I still have that question. Yeah. And I was, you know, as them, and, you know, I was part of that wave, right? Mm-hmm. Now, the question I have now, and the reason why I asked that to you is because I love the fact that you are bringing this new perspective as, you know, allow me to say that as a non-AEC person, mm-hmm. That I think it's exactly what the field needs. How do we avoid that with mm-hmm. AI, given the fact that I think there is a natural filter that is AI is actually complicated, right? That you have been explaining. And I love seeing all of this. But how do we avoid basically doing that, get back into the excitement, and then eventually, you know, falling down and...
Yeah. I don't know if we're going to avoid it. I don't know. I mean, I think that's it follows a lot of just technology adoption. I fear it might be human nature a little bit. We get really excited, and then we realize it's hard, and most of the people stop. But some of the people don't. And then in like, right, it's a huge up, it's a down, and then it's a slow increase of true value and productivity. I imagine we'll see something like that too here. I don't know. Yeah, I certainly don't know how we avoid it. I try to just temper expectations internally. You know, it's like that all the, you know, the stuff that you might be getting advertised is not as easy to move over here as they're selling you on it necessarily. And that's, you know, I mean, they're doing their job, right? And that's great, but it's also good to know just like, and you can make use of that, but it's a lot of work to some of the stuff that we've been talking about. So, and the value, if you get it to work, is real. Like, I think you can, you know, tons of industries have really had huge, you know, productivity increases. I mean, it depends, you know, what your personal goals of success look like, but from a business perspective, massive, massive success from adopting data science and AI systems. So I think it's proved out that it can work if done well and invested in. But it can be thinking that it's going to be just something just. I think there's a big risk of people burning out because they thought AI AI itself is going to solve their problem. And it will with a lot of help from you first. But once you solve its problems, it will help yours. So anyway, I don't know how we avoid it. Yeah. Yeah, and Sue.
Hey, Ben, can you hear me on this side?
Training GPT with language models are very energy intensive.
Okay.
Yeah.
Positive, the question
Still not working.
of know what kind of data is the structure of the data for AEC.
Mm-hmm.
Do you see a potential issue that like training it's not a language model, like X model for AEC is going to be very carbon intensive potentially, or do you
No, I don't. I think the reason that
repeat the question?
Oh, sorry. The question is essentially around, given that training GPT models, which are text, those kind of text models, so like ChatGPT, is so carbon intensive, do I think that training models for AEC would be equal or more carbon intensive? And I think no. I think part of GPT's promise and ChatGPT's promise is that it's trying to be exceedingly general. And I think the reality is, if you want to talk about general knowledge, the best representation we have of general human knowledge is text. Right, like if we want to know how somebody 1,000 years ago thought about something, we have one way really to know it, and that's through text. And we've been collecting so much text through the World Wide Web that we have so much of human knowledge in text. So when we're doing these kinds of questions, if we're not talking about AEC, we're talking about knowledge, text all of a sudden looks like a really good option for us. But it still has all of its weaknesses in that there's a lot of noise in text compared to signal. And that gap is, at least in my experience, where the computational cost can come in, because you have to look at so much more data to learn, because that noise is high, right? Like if I was trying to teach you a square from a circle, and I only gave you squares, circles, squares, circles, squares, circles, you'd figure it out. If I gave you square, and I told you that all you were going to be learning is squares and circles, but I start throwing in triangles, and I start giving you, like, you know, someone's dissertation, or right, like I start throwing in all this other stuff, you have to work a lot harder. So it works, and I think the intuition's similar. But I don't think there's so anyway, so to do architecture, I think if we get our representations right, and there's a cool paper outlining this, that you can perform better than like a GPT model on room function classification using a graph. So right, GPT is text, and so the difference is text versus graph. You can perform better with the graph after training for like 20 minutes. You can perform better than training with the GPT for like 5 hours, right? And so by getting this question right, we save ourselves a lot of money. We save ourselves a lot of GHG emission as well. So I think it depends on how well we can distill our information.
You want
to
undo your share and read the questions?
Yeah.
And maybe turn on your speaker, because your speaker and your mic should not be feedbacking each other. So turn my speaker on.
My speaker is on. Oh, my.
Yeah, we've got one person who wants to talk and ask a question. Let's go with the chat first.
Okay.
Just volume on your speaker. Everybody else evidently can.
Oh, I have this. So I don't know what's happening.
No, that's great.
Okay.
No, last question. All the way down at the bottom. That one.
Okay, I'll read it aloud so everybody out here gets it. Very interesting research and I'm a computational designer in Brooklyn. I understand the complexity of the model. How long did it take your team to reach this point? Oh, because I wanted to know what's the goal for now? And are you implementing research on real-time projects? And is the team growing and expanding? Okay, cool. A few parts of that. Did everybody get what I said out here? Okay, cool. So I joined DLR Group and pretty much started this team 2.5 years ago. So that's how long we've been working on these problems. The one we've been working on the longest is the point cloud problem. The other ones we've been working on for maybe a year, give or take. So the recommendation systems are newer. Then, okay. Well, the goal, really my goal and the goal of the team, I think is, in the simplest terms, is to kind of do this right and not skip any steps. Which I think a part of my philosophy around this, but just that I do think, and so I guess what that means in terms of like direct goals is we want to be teaching systems and building systems that understand architecture in similar ways to architects, so that it is right. So I'm trying to figure out the simplest way to explain this, but like ChatGPT is a language model. Some folks have probably heard that as kind of the term for it, and that's because it's a text-based model that is designed to be good at replicating language. And so I really do trust a GPT to write something for me, because that's what that model does. That's what it's supposed to do. That's what it's trained to do. And I really don't like to trust it for other things, because that is not what it's trained to do. It's not what it's supposed to do. Waiting to see, the peer-reviewed papers on whether or not it does really show some of these things, other capabilities reliably. But I think the real goal of the team is to build systems that directly understand and operate on architectural information, and can understand architecture in language and in the ways that architecture actually behaves. I don't know if that's super clear, but yeah, like our models should not be able to write you a very good essay, because that's not what we're designing them to do, I guess. But they should be able to design a darn good classroom, for example. Yeah.
You just kind of got me thinking there. Have you guys ever?
Oh wait, we have some things on real-time projects like the one I shared. We often are doing a lot of stuff in the back end that is then shared with designers. We have a few things that are in Revit live now, like the one I shared, and then the recommendation engines are going to be going in the next few months. So soon they will be on every project, but right now it is a little limited. Yes, sorry.
The point cloud products,
Yeah.
When you guys have that ready, please let us know. That'd be great.
Cool.
Because that's like the holy grail to BIM. But have you guys, for going back to the floor layouts and training the model to read images and stuff, have you guys ever considered maybe using robotics to actually teach a computer how to understand space by feeling it, or I don't know, being there? You're talking about how to teach a computer to be an architect, and
yeah,
I'm thinking actually experiencing the space could be something.
Yeah. The question was, have we ever tried to use robotics to help a computer essentially explore architecture for itself, right? I've not done that. That's a pretty good idea. It kind of falls into the realm of reinforcement learning. So if you are interested in that, you can look up reinforcement learning. And that, because that is, well, and the other one that's just kind of a tangent to this idea is letting a computer observe architects doing architecture. And both of them are building this data set not of like what's well, of strictly what's happening, not why, and letting the computer system try to learn why and when to do something. But I think it's the same intuition. It's like, let's let this thing just play around and see what it learns. One more question in the room, and then I'll do some from here too.
We talked a little bit about this before. Will an AI system that is maybe taking my model as its input, and then I'm asking it to do something with it, will it intuit what my model is without my having to do special things, like put things, make sure that it knows, you know, I'm identifying walls and types of spaces, or will it be able to use its own intuition to figure that out?
Yeah. So the question was, will an AI system be able to understand essentially my model, my input, without me having to do a bunch of work to kind of make it work with the system, quote unquote, right? So whether that's putting the right labels in the right places. I think yes. I mean, we've definitely shown, you know, like through like OpenAI systems, we don't have to tell a system exactly what something is for it to figure it out. You do, at a certain point, have to train the system on how to do that for itself. And at that point, you do really need to have labels. And so somebody's going to have to do that first before it knows what you're talking about. That doesn't mean it has to be the user eventually, right? But that is, at some point, you do have to label it and teach the computer what the labels are. And then it can do that nifty aligning for itself. I'm getting a lot of these. Thought this was supposed to silence when I'm presenting, but I guess it's not. Yeah.
Like when you're talking about training these models or going back to the floor plan, is there somebody like validating what it's coming up with? Is the human actually going through and being like, yes, this is correct.
Yeah.
Yes, this is a door. Yes, this is a window.
So that's right. We talked today about the input. So that's on the output side, right? So how do we know that the output is right? And so when we do it, we have our training data, right? So we've already developed, we have like maybe 5,000 examples of the inputs and the outputs. So that the input could be items that need to be in this floor plan, and the output is the floor plan, right? And so we have maybe 5,000, 10,000 examples of that input and output. And then this is super commonly done in data science, but you take like 60% of that data, and that's what you train the system on. And then you evaluate it on the data that it has never seen before, where you have the answer. So you already know, like, these are correct because you created it to begin with. And then you see like that this is like, 80% accurate or 90% accurate. That's a little simplistic because how you actually write that math on how to evaluate that can change depending on your problem. But that's the basic idea. Long term, definitely, it's good to have kind of human in the loop feedback, which is what you're describing. But at the point that we're at, kind of that human in the loop happens in the data set creation. That's when the human's in there validating that all of these training examples are good. And that's a big pitfall. When they're bad, then you're screwed. So it's really important to do the training data design. I want to just see, is there anything else?
Yeah, there's one more. From Opie. more than one.
Okay.
The first one was AT.
Okay. Can I speak on IFC, which is already computer-friendly language? Because I spoke to using something that computers understand, so why not use something that already exists? I agree. I would push back that IFC works with Revit and BIM authoring software, but specifically because we wrote a lot of software to understand that. The test to get that to kind of that you can use to see if it's computer readable is if I look at an IFC space, what number is that? And it doesn't make any sense, right? But if we look at an image, I can say it's what numbers is that, right? But I can say what numbers it is. If we look at text, right, with that encoding system, we can say what numbers is this. With a graph, we can say how many links does this have, right? We have like quantities and numbers associated with it. So that's kind of the difference. I think IFC has the beginnings, maybe, to be something that we could make computer readable. And it does fold into a graph quite well. So we would turn it into a graph, but then we still have to do our labeling. And if anybody wants to look up ontologies, it's really interesting, and that's also what we have to do. But OK. How soon can DLR Group employees try out this recommendation? I don't know. No, we're hoping in the next. Well, I'm hoping maybe in the next week or two, I'll be able to show a demo of it. I don't know if it'll be something that people can use. And then I'm hoping in the this quarter or next quarter, we'll have the beginnings of some of the recommendation engines in Revit. Can we volunteer to be beta testers? Yes, please. OK. Does the graph-style data structure have any benefit for conducting analysis versus traditional tabular formats? Or is it more for ease of use for the designer-researcher exchange between data formats? It has a lot of value for conducting analysis versus traditional tabular formats. The big reason is that a lot of the analysis we want to do in architecture, I think, is about flows and about relationships between spaces. And that's exactly what graphs directly speak to. So you couldn't run a noise diffusion simulation on a table. You can run it on a graph. You can do, you can use graph. You can input a graph and do like HVAC sizing. There's some good examples of that, right? It like really does a good job of describing the factors that are important in building, which is why I'm excited about it. We just still have some problems with it too. Yeah, Asher.
So you mentioned like data coming in from like tables and images and images for images to be read. But in BIM, for example, we have more than that. And
right.
We also have like a lot of vector information.
Yep.
Even prints that come out of vector-based programs like Revit and Autodesk.
Yeah.
Even in a PDF form, still retain a lot of that vector information.
Yeah.
Is there a way? Are you looking into ways to harness that data instead of trying to train on images?
Yeah, for sure. The question is how do we want to represent that? One other constraint for machine learning typically is that your data, and this might not make a ton of sense, but has to be the same size and shape every time. And so if somebody draws a wall, right, because if you're talking about vector, you're talking about points and lines and the things that are made with points and lines primarily. So you might have one image that can be made with 10 points and 9 lines, right? I think I did that right. 10 points and 9 lines. Or you could have a super similar thing made with like 10,000 points and lines, right? And so when you actually look at the data, it can be have super different sizes. Yeah.
But that's what the training is for. Meaning, if you have, let's say, maybe one family is 6,
yeah.
right? And then you train it on all of those different types. If one is a variation and a combination between those variations,
yeah.
you'll be able to recognize it.
Yeah. You actually need it to be the same size when you give it to the computer. But you can do it with, the way to do it is probably graphs also, because graphs natively support points and lines, which is what we're talking about when we're talking about vector. And then it's just about how you make, so you can do it with graphs.
When you have a lot of variation, you're training it on data, it'll basically be a scatter graph.
Yeah.
It has different approximate points outline of the image or item or whatever it's trying to recreate.
Yeah. Yeah.
And then I can kind of figure it out based on that.
Yeah, definitely. Yeah, it's definitely something we'll be looking into. I haven't done it yet, but yeah.
All right.
Cool.
That, I think, concludes the start of 2025. Thank you, Benny.
Yeah, thanks everybody for joining.
We'll be, as soon as I find the button here.